Let's build a simple circuit. We'll connect a switch to the VCC or plus voltage on one end. The other hand will connect via a resistor to ground, called a pull-down resistor. As a result, the button's output has a 0 if it's not pressed and 1 if it is. We'll connect this point to a SN74HC04N. This chip contains 6 NOT gates and is therefore called a hex inverter. Pin 1 is the input to one of the gates and the output goes to pin 2. We'll connect that to an LED. We'll connect the other end through a current limiting resistor to ground. This way, when the gate outputs a 1, the LED will turn on. And now we can see everything working as expected. When the button is not pressed, the LED is on. When we press the button, the LED turns off. This happens immediately. Or does it? To check exactly how immediate the gate works, we'll need an oscilloscope. We'll hook up the yellow probe to the input of the gate and the green probe to the output of the gate. To make things simpler to see, we set up the scope to only update when a trigger event happens. We'll set the trigger condition to the yellow input going from high to low. In scope language, we require that channel 1 has a falling edge. Since everything here works at about 5 volt, we'll set the trigger level to 2.5 volts, or as close to that as the scope will allow us. This means we capture the release of the button. Press the button, release it, and we get a nice clear picture. We see the yellow line going low and the green line going high at the same time. Cool. Except we can control the time resolution. We can tell the scope at what rate it needs to sample its inputs. Right now it's set so that each major horizontal division is 500 nanoseconds. This means that events that happen quicker than about 50 nanoseconds just won't show up. So let's ask for a higher resolution. Setting the resolution to 50 nanoseconds per unit, we're beginning to see that the picture isn't as straightforward as it first seemed to be. We're beginning to see ripples, both in what our button is producing and in the gate's output. Setting the resolution to 2 nanoseconds per unit, things are no longer very clean at all. It's obvious that the input voltage takes some time to come down and that the output voltage takes some time to come up. But how much? More specifically, the picture is so messy it's not clear where to start our measurement and where to end it. Luckily, the chip's datasheet is readily available and comes to our rescue. The section called Recommended Operating Conditions tells us what the chip would consider valid inputs. The table is divided based on the operating voltage of the chip. Our voltage is at just a little over 5 volt, which is between the 4.5 volt and 6 volts listed in the datasheet. To give our chip the fairest chance, we'll use either the 4.5 volt or 6 volt value in such a way as to minimize the measure time. We begin our measurement when the input voltage officially becomes a 0. We can see that a valid 0 is when the input voltage is below 1.8 volt if the supply voltage is 6 volt and below 1.35 volt if the supply is 4.5 volt. Since we're measuring falling voltage, we'll set our start of measurement to when the voltage crosses the 1.35 volt threshold. Again, we're trying to give the chip the fairest shake we possibly can. The easiest way to set the start this way is to set the trigger level to that or thereabout. This way, the point at which the input was first below 1.35 volt will always be at the dead center of the screen, as that's where the scope places the trigger point. But wait, the same datasheet also specifies the requirements for a 1 input. It says that a 1 has to be above 3.15 volt or 4.2 volt depending on supply voltage. What happens when the input voltage is lower than 3.15 but higher than 1.35? Technically, this condition is called a bus violation and is illegal. A moment's thought, however, will lead to the conclusion that such voltages are unavoidable. Zoom in enough on the timescale, an instant transition from above 3.15 volt to below 1.35 volt is simply impossible. What we do instead in such a case is absolve the gate from any responsibility for the output. It is allowed to output anything when the input is invalid. This is the reason we only start the measurement once the input voltage goes below 1.35. We have no guarantees before that point. We can see that at the center, which is the point the input first became a deterministic zero, the output is still pretty low. It takes a while for the output to rise enough. But how much is enough? Once again, the datasheet comes to our rescue. The section labeled Electrical Characteristics lists the voltages we can expect from the chip. We see that when the chip is outputting a 0, the voltage should be below 0.1 volt, and when outputting a 1, it should be above 4.4 volt. Actually, these lines say that when the output is feeding a load, such as lighting an LED, the voltages might be different. So now to escape the serpent's tongue, we shall disconnect the LED erlong. I know my iambic pentameter needs work. So let's set a marker for 0.1 volt and for 4.4 volt. We're looking for the time between the middle of the screen, which is the input register in definite 0, and the output going above 4.4 volt. We can see that the graph changes quite a bit between attempts, but is consistently above 7 nanoseconds. In other words, even once the input goes to 0, the chip takes at least 7 nanoseconds to rise to a value that can be considered a valid one. In other words, the gate has a delay in producing a correct result. By the way, the switching characteristics section of the datasheet also has information about the propagation delay, which is how long we can expect that to take. At 4.5 volt and at room temperature, it says it can take up to 19 nanoseconds, but that we should typically see around 9 nanoseconds, which is pretty much what we indeed see. Hooray for datasheets. One last point before we move to FPGAs. If we have multiple gates in sequence, the propagation delay gets summed up along the path according to the math we just did, from the point the input register a definite 0 or 1 until the output register a definite result. Each gate contributes its own delay. We cannot do anything with the output until all gates in the path have stabilized. This is the SR latch we showed in the previous video. When we input 1 on the set input, Q goes to 1 and Q bar goes to 0. If we input 1 on the reset input, Q bar goes to 1 and Q goes to 0. If we input 2 zeros, it just continues to output the last state it was set to, and inputting 2 ones is illegal. The latch remembers its state by introducing a loop that includes both NOR gates. Simple. But remember, each of these gates has a propagation delay. Let's see what happens if we input 1 on the set input, except we do it very briefly. In particular, what happens if we input a 1 just long enough for it to propagate only one of the NOR gates? So the set input goes high, causing the top NOR gate to go low. This causes both inputs of the bottom gate to go to 0, causing the bottom gate to output a 1. But just as that happens, the set input goes back to 0, which means the top gate also gets 2 zeros and also outputs a 1. And now both gates are 1, which means that both gates also receive a 1 input. This causes both gates to go to 0, except now both gates receive 2 0 inputs, causing them both to go to 1 again. In the previous video I said that for all legal inputs, Q and Q bar will output opposite values. Here we see that despite never giving it the illegal input of 2 ones, Q and Q bar output the same value. Worse, they don't serve as memory, they're just flickering. If we only gave it legal values, why does it misbehave? The answer is that we did not, in fact, give it legal values. 2 ones is not the only illegal input. Giving it a 1 pulse that is too short is also illegal. As mentioned before, for combinational gates, the term to look for is propagation delay. When a clock is involved, we're using a slightly different terminology, however. Since the register does not respond to its input until the rising edge of the clock, we are insensitive to any flicker that happens until the clock rises. Even so, as we've seen, this response isn't instantaneous. We do in fact need the inputs to the flip-flop to be stable enough time before the clock arrives, and sometimes a little after it arrives as well. The clock does allow the inputs to fluctuate, but they must settle down a certain amount of time before the clock rises. The time before the clock that the inputs must be stable is called setup time. The time after the clock in which the inputs must remain stable is called hold time. In modern components, the hold time is often 0, but the setup time is real and unavoidable. Last video we built a clock divider. One of the paths there included a series of flip-flops storing a counter and combinational logic performing a -1. Obviously, this combinational logic has propagation delay. Up until now, we've just assumed everything will be ready in time, but it's now time to stop and ask, will it? Let's break that question down. What we're asking is this. The flip-flops will also have propagation delay, i.e., time between the clock and the flip-flop's outputs showing the new values. Does this delay plus the propagation delay of the combinational logic mean we're ready with the new values enough time such that we have setup time of stable inputs to the flip-flops before the next clock arrives? The answer, of course, depends on the properties of the hardware unit in play. It also depends on the clock. It even depends on the length of the paths connecting the LUTs and flip-flops. It seems crazy that we should have to calculate it ourselves. You'd expect the development tool to do this for us. Which begs the question, why doesn't it? The answer is that Vivado tried. It really tried. But it failed, and that is entirely our fault. To Vivado's credit, it did give us a list of problems with our design. Some of them are the reason it failed to calculate timing, and we just ignored them. So let's resolve them all now, and by all, I mean a small subset of them that happen to be interesting for this video, of course. The synthesis stage is where the hardware descriptor language code is turned into physical elements, LUTs, flip-flops, and so on. We can see that that stage produced 2 warnings. The first is not really a warning at all. It says, parallel synthesis criteria not met. This is just a message from Vivado saying that while it is configured to use multiple CPUs when performing synthesis, and the computer indeed has multiple CPUs, it won't use multiple CPUs because it decided it will not save on synthesis time. There's no action item attached to this warning, and it does not affect the end result in any way, shape, or form. The second warning says, design blink has port that other LED driven by constant 1. Twice. This warning actually has some potential usefulness. There are cases where you think you wrote logic driving an output pin, but either through optimization or mistake ended up driving it with a constant. In that case, this warning might point you to a bug in your design. Of course, in our case, we did it on purpose. That other LED is connected to an LED, but we have nothing to say on it, so we put a 1 on it so it'll be off. Not as useless as the previous warning, but still not helpful to us. Which brings us to the implementation stage. This stage is sometimes referred to as PNR, or place and route. In this stage, Vivado takes the list of hardware blocks that the synthesizer concluded are needed and matches them with actual physical elements on the FPGA itself, a process called place. It also maps connections between those physical components. These connections are called nets. That process is called route. Place and route, PNR. The placer produced this warning. Timing had been disabled during placer, and therefore physical synthesis in placer will be skipped. This is very useful. It tells us that since timing analysis has been disabled, the physical synthesis will not take place. This is exactly what we've been looking for. Okay, on second thought, maybe not. We already knew timing analysis was disabled. It doesn't tell us why. Moving on. Which brings us to the router. Here, finally, we're getting warnings with actual useful explanation of what's missing. The first warning says, No user-defined clocks were found in the design. Power estimation will be inaccurate until this is corrected. We were not complaining about the power estimation, but okay. It even has steps to fix the problem. Please specify clocks using create clock, create generated clock for sequential elements, or something. That seems useful, but let's circle back to this. Let's look at the second warning, which drives straight to the heart of our problem. There are no user-specified timing constraints. Timing constraints are needed for proper timing analysis. Finally, we have the root of the problem. So what happened here? We wanted Vivado to analyze our circuit for timing. What we failed to do, however, is tell it what's expected of it. In other words, Vivado says it cannot test whether our design meets timing requirements if we don't tell it what the requirements are. In a nutshell, timing constraints are instructions for the FPGA on how external pins should behave. In particular, it tells what performance is expected of the output pins and what to expect on the input pins. Setting constraints on external pins will actually have to wait for a later video. At this point, we're more interested in the propagation delay between the output of an internal flip-flop and the input of another internal flip-flop. Technically the same flip-flop, but strangely that doesn't matter. What do external pins timing constraints have to do with anything? The answer is that to calculate whether the propagation delay is fast enough, Vivado needs to know one crucial bit of information. What is the speed at which the input clock beats? And since this is an external pin, Vivado treats it as a timing constraint. We need to tell Vivado what to expect on it. It's now time to define the input clock. In a move that may put some of my longtime viewers in clinical shock, I'm going to use the wizard in order to do that. Viewer discretion is advised. The wizard correctly detects that our input, called clock, is a clock. Surprisingly, or you know what, maybe not, it does not do so based on the name. Instead, the trigger for this detection is that this signal is directly connected to the clock input of a flip-flop. In Verilog terms, the signal is used in the sensitivity list of an always FF block. Here's a riddle for you. Aside from clock, the sensitivity list also includes reset. And yet, reset doesn't appear in the wizard's list of clocks that need definition. Don't get me wrong, reset shouldn't appear as a clock, but how did Vivado know it didn't need to? Sadly, I won't be discussing the answer to this question in this video, but please believe me that an answer is in the planning. I just want to reiterate, to remove all doubt, that the signal's names have nothing to do with it. Back to the clock definition, we let the wizard know that this is a 50 MHz clock and it fills in the rest of the values. The wizard also shows us the line it is going to add to the constraint file. This line reflects the same information in the wizard. For now, we hit skip to end and apply. We can see the clock definition line added to the constraints file. When we regenerate the design, we see some things have changed. First, we see that both place and route warnings are now gone. With a clock defined in the design, timing can be analyzed. The design summary page also looks quite different to before. For one thing, as promised by the warning we solved, the power estimation is now considerably lower. Furthermore, the methodology tab that previous had 27CW, standing for critical warnings, now has just 2 regular warnings. Furthermore still, the tabs labeled WNS, TNS, WHS and THS that used to have NA now have numbers marked in black. So what is this about? Vivado calculates how long after the clock the combinational logic, in our case the subtractor, produces a stable output. It adds it to the flip-flop setup time requirements and subtracts that value from the clock period. The result is the slack, by how much we can make the design slower and still not be in timing violation. If the value is negative, it means we're already in timing violation. This results in two values of interest. Worst negative slack, or WNS, is the smallest slack we got over all nets. Of course, if the slack is negative, smallest is the biggest in absolute value. If this value is positive, as is the case for us, then there is no propagation time violations in our design. Total negative slack is the sum of the slacks over all nets that are negative. In general, WNS tells you how big of a problem you have. You can think of it as either by how much time do you need to make things quicker to bring them into compliance, or by how much do you need to slow the clock in order to be in compliance. TNS, by contrast, gives you an indication of how widespread the problem is. If the TNS is the same as the WNS, you know there is just one path that is in violation. If it's much more negative, it means your problem is spread among multiple nets. For this video, we'll skip the discussion of WHS and THS. They have to do with multiple clocks and external pins constraints, two subjects we won't be covering this time. So what does a WNS of 16.43 nanosecond mean? Taken literally, it means we can shorten the clock period by 16.43 nanosecond and still have it barely meet requirements. Our clock is currently at 50 MHz, which is a period of 20 nanoseconds. If we shorten it, we get a clock period of 3.57 nanoseconds, which theoretically means we can speed the clock up to a little over 280 MHz and still have the requirements met. Of course, we only have the 50 MHz clock, but we can change the constraints to make Vivado think that the period is shorter, i.e. the clock is faster. The viewer could be excused to think that this would result in a WNS of about 0. Instead, we got a WNS of over half a nanosecond. How come? The answer has to do with the PNR algorithm. There is no straightforward algorithm for finding the optimal place and route. By which I mean there is, of course there is, but it is a very inefficient one. Very, very inefficient one. In fact, it belongs to a group of algorithms called NP-complete. It is so inefficient that there is no point in running it on any non-trivial design. Instead, the implementation engine employs a heuristic algorithm that does a best effort attempt at efficient placement. In other words, the more time you spend on generating the design, the more efficient the result is going to be, at least statistically. So if the design already passes its constraints, there is probably little point in spending more processing and user time on a more optimized design. That only makes sense if the design isn't passing. So when we gave the design a narrower slack to work with, the design took longer to place, but that resulted in better margins and better timing. So what will happen if we try to use a design that is really violating timing requirements? The answer is, it depends. Of course it does. Of course, we don't actually have another clock beside the 50 MHz one, but we can generate one. An FPGA has clock modifier components. The two most common are phased lock loop, or PLL, or a more generic component called mixed mode clock manager, or MMCM. For our use case, the two are the same. Without going into how they work, both can take an input clock and then perform a series of divisions and multiplications on its base frequency to achieve almost any other frequency we want. Of course, we don't have to calculate these divisions and multiplications ourselves. We can use a wizard to calculate them for us. So we'll use Vivado's clocking wizard. We set the input clock frequency to 50 MHz. We'll set the output clock as high as it would go, in this case 800 MHz. We'll also be connecting our board's reset to the MMCM. Since our reset is active low, we'll set the MMCM's reset to be active low. So our MMCM inputs include the reset pin and the source clock, and the outputs include the high frequency clock, as well as a pin called locked, which tells us the output clock is stable. We'll add this new model to our design and connect the board's clock and reset to the MMCM. We'll also define a wire to carry the high-frequency clock and locked signal. As far as our always block, the high-frequency clock is the input clock and the locked signal is the reset indicator. This way we won't start counting with an unreliable clock. To make everything even have a chance of working, we need to hook up one more thing. This FPGA has no clock buffers that can accommodate this higher frequency. Without going too much into the weeds, a buffer allows a single source to reach more elements on the FPGA itself. Since we only need it for one place, losing the buffer isn't a big deal in itself. It does, however, require us to manually add a feedback loop for the MMCM to lock on the target frequency. With everything in place, we synthesize and get timing violations, as well as a bunch of other violations. If we take the negative slack at face value, it seems to say we should reduce the clock from 800 MHz to 330 MHz to be in spec. We're over twice the frequency our FPGA can actually support. So what would happen if we try to load this core, violations and all, to the board? Guess what? This obviously doesn't work. The LED is blinking way too fast. In fact, it's blinking so fast I'm not even sure you're getting the blink rate on the video. We're at 16 Hz instead of 1 Hz. Actually, that sounds oddly familiar. We've set the counter to divide the input frequency by 25 million precisely so we can turn the 50 MHz input clock to a 1 Hz output. But now we've put in an 800 MHz clock, but we still divide by 25 million. A 16 Hz blink is what we're supposed to get. So let's fix the divider to work with an 800 MHz input clock. Synthesize, and to absolutely nobody's surprise, the timing violations didn't go anywhere, and if anything are now even worse. This makes sense, as we're now counting to 400 million instead of 25 million, which means we need 4 more bits to store the counter. This is also reflected in our flip-flop use. But what happens when we load it? It would appear that everything is working. What? To the naked eye, it would appear we got an LED blinking at 1 Hz, precisely what we expected. But if we're having timing violations that require a clock less than half the frequency we're actually giving it, how come everything is working? There are 3 possible answers here. The first is that we don't know this is actually working. If you look at the combinational loop that violates timing, it is possible that on some cycles the update doesn't happen in time. If those cycles happen rarely enough, we may have an LED blinking at a rate just lower than 1 Hz, but with an error too small to measure with by meager, i.e. cheap, equipment. But even if this is really working, it doesn't mean it will remain working. Some aspect of any chip's functions are affected by environmental factors, chief among them temperature. It's possible that the design works at room temperature, but not at higher temperatures. In particular, it is possible that the heat the FPGA itself emits will, at some point, heat it enough to cause it to stop working. Vivado knows the tolerances the FPGA can work with and is calculating for the worst case. It's also possible that there is some variance between different FPGAs from the same series, and we have a core that loads and works on this particular chip, but may not on others. But even if this works under all temperatures, we're still not out of the woods. When you're using a design with violations, either obvious like here or hidden as a result of not defining the constraints and therefore disabling Vivado's verification, you're in danger of being sensitive to placement. As I said before, the placement of nets and logic inside the FPGA is non-deterministic algorithm. It is sensitive not only to the relevant parts of the design, but to the whole thing. When I originally implemented the SPI controller in CompuSAR, I left some signals without timing constraints. Everything worked perfectly, at first. But then I made a change to a completely unrelated part of the design, and all of a sudden the SPI controller broke. It was no longer able to communicate with the flash. I could trace exactly what unrelated change I made that broke the SPI, but as I said, it was unrelated. It was just impractical to work around the problem. I ended up biting the bullet and rewriting the SPI controller the correct way. The lesson here should be this: never leave your timing constraints undefined. If you have a timing violation, fix it. In the next video, we'll talk about clock domains and metastability. In the meantime, thank you for watching.